look inside a complex machine, like a car's transmission or even an old-school clock, and you see that incredible dance of interlocking parts, it looks so elegant, right? But here's the thing. Teaching a computer to understand that physical dance just by looking at a static 3D model, that is one of the toughest nuts to crack in AI perception today. So that's what we're diving into. How we can teach an AI to finally understand the physics of motion, starting with one of the most fundamental inventions in all of engineering, the gear.
So here's our game plan. We're going to start with the basics, really get our hands dirty with what makes gears tick. Then we'll learn the lingo. After that, we'll jump into the deep end and tackle the huge problem of predicting motion. We'll meet the AI built for the job, Dynamo, and see how it stacks up. And finally, we'll zoom out and look at what this all means for the future of how we design and build everything.
And hey, if you've ever felt like Reddit user King Mahem here, you are definitely not alone. Figuring out how all these pieces are going to move together isn't always intuitive, even for us humans. So just imagine how much harder it is to teach a machine that has zero intuition to start with. This right here is the perfect jumping off point for our story.
All right, so before we can get to the mind-bending AI stuff, we gotta start with the fundamentals. Let's talk about the humble gear, the building block of pretty much every complex machine out there.
When you boil it all down, gears are these beautiful, simple machines that do three really important jobs. First, they can change speed, making things spin faster or slower. Second, they can alter force, or what we call torque when things are spinning, to give you more power. And third, they can redirect motion, sending that power around corners and into all sorts of nooks and crannies.
Now here's the crucial part, the one rule you can't break. It's all a trade-off. You can't have everything at once. Just think about riding a bike. When you're struggling up a massive hill, what do? You shift into a low gear. Your legs are pedaling like crazy, but the wheel turns slowly, giving you that extra force, that torque, to make it up the climb. Then, when you're on a nice flat road, you shift to a high gear. Now you're pedaling slower, but that wheel is just flying. You're trading force for speed. That simple principle is the absolute heart of every gearbox ever made.
Okay, so to really talk about gears and understand what's going on, we need to speak their language. Let's cover a couple of the absolute key terms.
The most important concept, the one thing you really got to know, is the gear ratio. And it's actually super simple. It's just the ratio of the number of teeth on one gear compared to the number of teeth on the gear it's connected to. So if you have a big gear with 40 teeth driving a little gear with 10 teeth, that's a 4-to-1 ratio. That means the small gear is going to spin 4 times faster, but it'll only have 1/4 of the force. This one little number dictates the entire outcome.
And as you can see here, gears come in all shapes and sizes. It's definitely not a one-size-fits-all situation. You've got your basic spur gears for straightforward power transfer. You've got these clever bevel gears that can turn power 90 degrees, which is what you find in a car's differential. And then you've got these awesome rack and pinion systems that do something that feels like magic. They turn spinning motion into straight line motion. Every single design is a specific solution for a specific problem.
Okay, so we humans can look at these gear systems and, with a bit of thinking, we can pretty much figure out how they're going to move. But how in the world do you teach a computer to do that just from a static 3D model? This is where things get really, really interesting. So the core of the problem is predicting something called coupled motion. What that means is that in a system like this, no part moves on its own. The movement of one gear directly forces another one to move. It's a chain reaction. A computer can't just look at one gear and guess its speed. It has to understand the entire web of relationships, all from a single, motionless snapshot. That's a huge challenge. And to teach an AI something new, you need data, a lot of it. And that, it turns out, was a massive roadblock. As you can see from this table, the datasets that existed were full of things with simple, independent motions, like a cabinet door or a laptop hinge. They had almost zero examples of this complex, coupled motion. So to fix this, researchers had to build a brand new dataset from scratch. It's called MechBench, and it's filled with hundreds of different gear assemblies, made specifically to teach an AI how these parts all depend on each other.
So with the problem clearly defined and the right data finally in hand, it was time to actually build the solution. So let's meet Dynamo, a brand new AI model designed from the ground up to predict motion in these incredibly complex systems.
The way Dynamo works is actually pretty elegant. It's a 3-step process. First, it uses a part of the AI called PointNet++ to look at each individual piece and just understand its basic shape. Then, and this is the key part, it uses something called a graph neural network, or GNN, to figure out all the connections. Which parts are touching, how are they related, and once it understands those relationships, it passes that info to a transformer model, which then predicts the motion of every single part through time.
And here is what that whole process looks like under the hood. You can see the raw shapes of the parts going in on the left. Then that critical GNN module in the middle does the heavy lifting, figuring out how everything is coupled together. And finally, over on the right, the transformer takes that understanding of the relationships and basically decodes it into a full movie of how everything is going to move. It's a complete pipeline, from a static picture to a dynamic prediction.
So the theory is brilliant, the architecture is slick, but the real question is, does it actually work? Let's take a look at the results.
Wow, this chart pretty much tells the whole story. What we're looking at is the average error in degrees when predicting how a gear will rotate. An older method was off by almost 16 degrees. That's a pretty big miss. A more recent model got it down to about 6 degrees, which is better. But look at Dynamo. It cuts that error almost in half again, down to just over 3 degrees. That is a massive, massive leap in accuracy.
And here's what that accuracy actually looks like. It's one thing to see the numbers, but this is something else. On the left is the motionless model the AI started with. On the right, the blue is the ground truth, what really happened. The red is Dynamo's prediction. I mean, look at how perfectly they overlap. In this entire complex system, the final error was just 1.6 degrees. It's practically flawless. And what's even crazier is that it can handle totally different kinds of motion. Check this out, a rack and pinion system. Dynamo correctly figured out that the spinning of the gears should create a straight line, linear movement in the rack. And again, just look at the alignment. The predicted red is almost exactly on top of the actual blue. This is incredibly difficult to do, and it just nailed it.
So this is so much more than just a cool academic experiment. An AI that can look at a machine and intuitively understand how it works, that has some pretty profound implications for how we're going to design and build things in the future.
So what does this actually mean for the real world? Well, imagine your CAD software not just letting you draw shapes, but actively understanding the function of what you're designing and simulating it for you in real time. Or think about robots that can walk up to a piece of machinery they've never seen before, understand how it works just by looking, and then actually use it. This kind of tech means faster prototyping, saving engineers thousands of hours they currently spend setting up simulations manually. And all of this leads to one final, really big question. For all of human history, design has been about people translating a function they want into a physical form. But if an AI can do the reverse, if it can look at the form and instantly understand the function, what does that mean for the future of engineering and creativity itself? What happens when we can ask an AI not just to test our design, but to come up with a better one from scratch? That, right there, is the new frontier this research is opening up.